Hello, I'm Ahmet Emre Gökpınar. I'm responsible for the first half of the project. We started GradCam, which asks where the network looks when predicting uncertainty. As you can see, it consistently lights up on textured surfaces like brick facades, cable drums, structural edges. These are the places where stereo matching gets difficult. Also, textured poor regions like sky receive the attribution which is expected. Next, we check if blur or contrast can predict failures. Since it's a synthetic data, blur gives R of 0.059, very close to 0. But more interestingly, the 5 worst frames all land between indices 276 and 300. That's not a general image problem, but local, because there is an aggressive viewpoint change between those indices. For calibration, the beam uncertainty curve is flat, but the KS test still shows low and high uncertainty frames have significantly different error distributions. D of 0.128 and P of 0.006. So the signal is there, but the proxy is very just weak. And finally, key point density map shows a clear center bias. Accepted key point sits 20 pixels further from the border than rejected ones because border regions have poor stereo overlap.
Hello, my name is Bishir, and I'm going to take the narration from here. Here we switch to the real data, which is Euro C, and it's a machine hole sequence. Let me show you the video of it. It's basically a machine hole captured from a UAV, and it's a real sequence, not a synthetic one like Tartan we used in the previous notebook. Okay, let's turn back to the notebook. So we go stage by stage through the pipeline here. At the front end, we compare the easiest and the hardest frames by predicted covariance. The hardest ones all land between 1600 and 2500 frames, which basically corresponds to the dark parts of the hole. So we can actually name and locate where the system struggles. For the key point selector, we build a rejection map. The bright parts corresponding to the areas where the rejection mostly happens. And the rejection percentage is 0.73 on the right border and 0.70 at the bottom. We observed the same center bias in previous dataset, Tartan with a completely different fisheye camera. So this result should definitely caused from the learned covariance itself. Then for the backend, we first decompose drift by axis and then run lime. The lime perturbation works like this. For each of the 20 segments in the trajectory, estimated trajectory, we artificially worsen their frame coordinates by adding small noise. Then measure how much the global trajectory error increases. You would expect the already bad segments to matter most, but the opposite happens. The segments with the lowest error, highlighted in the red here, cause the biggest error increase when perturbed. So that's another interesting finding. Finally, feature attribution over 307 frames, and the blur is the top predictor at score of 0.42, which was 0 on synthetic data because there is no blur in the synthetic data. So on a real camera with fast motion, blur is the dominant failure mode. And I want to remind that we compute blur as the inverse of the Laplacian variance. It's a single matrix operation on a grayscale image. It just takes microseconds. So in a real UAV deployment, we could compute it on every frame, and if the image is too blurry, we can flag that frame's pose estimate as unreliable before passing it downstream. So these are the overall explanations of the experiments we performed. For more detail, you can read the final report. Thanks.